I'm talking about, again, emphasizing the relationship between what we call, what we traditionally thought of as probability, and now we're looking at functions, right? So the area under a probability density function, the area under the whole function that we're looking at, right? That's basically the sum of all the probabilities. And what do the sum of all the probabilities have to equal to? When you think about, they have to equal to 1, right? Because 100%, that's a certainty. So the area under probability density function is 1. But this is where I said that we need to think about the relationship between now what we traditionally thought as a separate topic, functions and calculus, and we now want to think about how does this relate to this concept of a probability density function. So areas under a curve, when did we study that? What do we call that? Integration, what other one? We call it integration. And if you want to think about this, representing this in terms of our notation, if this is our function f of x, if I'm going to take the integral of f of x with respect to x, right, we can say that that's equal to 1. The other thing I want to talk about is usually we have bounds for our integrals, right? Like from a to b or whatever. But for a probability density function, we kind of extend that. We actually say from negative infinity to infinity. This is a property of a probability density function. I feel like, and I will double check this, I do think we could just as easily say a to b and where a to b is the domain upon which is defined, because probability density functions, they will typically be restricted between certain values, and I'll tell you why in a moment, right? But just as easily, we could say between a to b, okay? So just note that down for me. Okay, I just want to show you some examples of these probability density functions. So I emphasize that the idea is there are particular things that have to be measured as continuous data. Now, mixed in between these are ones that are discrete, and hopefully you can tell the difference, right? For example, number of heads, that has to be a discrete quantity. It has to be a whole number quantity, right? But there are things which are not discrete. So have a look at this. The birth weight of newborn babies, for example, right? So can you see that they have the records, obviously the records they will probably take as a whole number, but what they tend to do is they approximate it using this curve. And that's what we call a probability density function, yeah? Galton board, if you remember from last time, was the actual board that makes that normal distribution, right?
What?
Other kinds of things, average height of NBA players, blood pressure, all of these are, I guess, I suppose, kind of continuous values that you can take. And that's why we need to actually take a curve to approximate these. We can't just use these bars anymore for all of them, okay? We do need to use a continuous measure for that. That's just like some real world examples of why we might use that. Let's have a look at some questions, right? So here's the first question. Show that this is a PDF, right? So what was the property that we said has to be true? Upon the domain which it is defined, the integral has to equal to 1, right? So let's check that out. So can you see how their definition they give you? Now, this is what we call a piecewise function. It's a fancy, you might remember this from the 11. It's a fancy word for basically saying what's happening on some particular x values, what's happening elsewhere. So can you see how this function is only defined from 0 to 4? So that's how I'm going to check whether this is a PDF. If I take the integral of this function, and I want to verify that's equal to 1 when I do this. So integrals, hopefully we're really good at that now. Can you tell me, Christian, what do I want to do with this x cubed function? How do I integrate this guy? Because I was feeling mean. So, how do you usually integrate? What's the first thing we usually think about? So looking at the x cubed, imagine it's just x cubed. Right? What would you do with it? Yep, that's right. So if you want, you can take that constant out as well, if that helps. Right? It's not. Is it going to be 1, you reckon? Let's have a look. So the 1 over 64 we can keep there. And then we raise the power x to the 4, we divide by the new power, which is 4. And we go from 0 to 4, then we evaluate it by substituting in x equals to 4. And in fact, the constant here you might want to take out. That's a trick that I would usually do. It saves me a bit of time. So we get 4 to the power 4 on 4 minus 0 to the power 4 on 4. And I always still write out, even if it's 0, I always write it out, because particularly in like trig examples, exponentials and things like that, you often get it not being equal to 0. So that's something to make a note of. Here's the one. Well done. Good job, man.
Let's go.
So what I want to show you now, I want to show you the graphical representation of this. So this is what it looks like graphically. Yeah, you can see that if you look at this, the area between the whole area is 1. Now something that again is relating to that thing, this idea that the probability of a single outcome is 0 can be seen very clearly with this graph, right? How do you see that? What's the probability of a single outcome? Like what's the probability that 4 occurs, for example?
1.
I know, I had to do GeoGebra because Desmos didn't have this applet. If I was thinking about the probability that 4 would occur, if we're thinking about areas, right? The probability that 4 should occur should be this little sliver that appears, right? When I get to 4. But the question is, because if the area is related to the probability, what's the area of this little line here? Well, there is no area, right? So this is, again, an emphasis that the probability that one single outcome can occur is actually 0. Because if you relate it back to integration, right, we remember that we called this little width dx, like a very infinitesimal small width. So if you're multiplying 0 by this value here, it's essentially just going to be 0, right? So that's just another way of thinking about it. So what that means is we can't actually find the area of a single outcome, but what could we do? We could find the probability that, that's right, exactly right, the range. So if it lied between, see if I can get my slider right. Oh, I was trying to get 2. Oh, got it. So the probability that it goes from, that the outcome is from 2 to 4 is quite high. It's like 93%. So this is the idea behind it. If you want to find the probability of a range, you can do that, but we can't find the probability of one single outcome. Okay, so that's something I want to emphasize. Yeah. Let's look at another question.